Today we're going to explore one of the most profound examples of scientific discovery through experimental measurement. We'll examine the work of Gerd Binnig and Heinrich Rohrer, who revolutionized surface science with their invention of the Scanning Tunneling Microscope. In 1981, two physicists at IBM Research Laboratory in Zurich, Switzerland, were working on a seemingly impossible problem. They wanted to see individual atoms on surfaces. Gerd Binnig and Heinrich Rohrer formed a partnership that would change the course of science. Their collaboration was driven by a simple yet profound question: can we actually see atoms? But why was this such a difficult problem? To understand, we need to consider the scale we're working with. Let me ask you a question. How small is an atom? Consider this. If you could magnify an apple to the size of Earth, the atoms in that apple would be roughly the size of the original apple. That's the scale we're dealing with. An atom's diameter is approximately 10 to the power of -10 meters, or 1 angstrom. This is far beyond what conventional optical microscopes can resolve. Traditional light microscopes have a fundamental limitation called the diffraction limit. The resolution limit of a microscope is approximately wavelength divided by 2. For visible light, this is around 200 nanometers. 200 nanometers is much larger than 0.1 nanometers, which is the size of an atom. So light microscopy simply cannot resolve individual atoms. Binnig and Rohrer had a brilliant insight. Instead of using light, they would exploit a quantum mechanical phenomenon called electron tunneling. What is quantum tunneling? In classical physics, a particle cannot pass through a barrier if it doesn't have enough energy. But in quantum mechanics, there's a probability that a particle can tunnel through a barrier, even without sufficient energy. Here's a visualization. An electron approaches an energy barrier. Classically, it should bounce back. But quantum mechanically, there's a probability it will appear on the other side. This is tunneling. The tunneling current I is proportional to e to the power of -2 kappa d, where d is the distance. Notice the exponential dependence on distance. This exponential dependence is absolutely crucial. It means the current changes dramatically, with tiny changes in distance. This gives us extreme sensitivity to surface topology. Now let's understand how Binnig and Rohrer set up their experiment. The Scanning Tunneling Microscope has several key components. The microscope consists of an atomically sharp metal tip positioned extremely close to a conductive sample surface. We're talking about a gap of only 0.5 to 1 nanometer. A small voltage is applied between the tip and sample. A critical requirement is that the tip must be incredibly sharp, ideally terminating in a single atom. This ensures that the tunneling current comes from a well-defined point. Now let's examine the actual measurement process. There are two primary modes of operation for a scanning tunneling microscope. In constant height mode, the tip scans across the surface at a fixed height. As it encounters atoms, the gap changes, causing the tunneling current to vary. The tip moves in a straight line, while the surface topography varies. The current fluctuates based on the tip sample separation at each point. In constant current mode, a feedback loop adjusts the tip height to maintain a constant tunneling current. The height adjustments map out the surface topography. When Binnig and Rohrer first began taking measurements, they started with relatively simple surfaces. Let's look at how they collected and analyzed their data. What makes a good test surface for initial experiments? You want something with a well-known atomic structure, high electrical conductivity, and chemical stability. Gold and silicon were popular choices. Here's a representation of early data. On the x-axis, we have position along the scan line, measured in nanometers. On the y-axis, we have tunneling current in nanoamperes. With data in hand, the next step in the scientific method is to create a theoretical model. Binnig and Rohrer needed to understand exactly what their measurements represented. They started with the basic tunneling equation. Current as a function of distance d equals I sub 0 times e to the power of -2 kappa d. The decay constant kappa equals the square root of 2 meters phi divided by h bar, where m is electron mass, phi is the work function, and h bar is the reduced Planck constant. For typical metals, kappa is approximately 1 per angstrom. This means the current decreases by a factor of e, approximately 2.7 for every angstrom increase in distance. Let's visualize this exponential relationship. This is crucial for understanding the sensitivity of the technique. This graph shows normalized current versus distance. Notice how steeply the current drops off. An increase of just 1 nanometer reduces the current to about 14% of its original value. As Binnig and Rohrer refined their technique and examined different surfaces, they began to observe anomalies, data points that didn't fit their simple model. These anomalies led to profound discoveries. The first anomaly involved unexpected variations in current that couldn't be explained by simple topography alone. Some atoms showed much higher or lower current than expected based on their height. What could cause this? The answer lies in electronic structure. Different atoms have different electronic density of states near the Fermi level. The tunneling current depends not just on distance, but also on the availability of electronic states. A more complete model includes the local density of states ρ sub s at the Fermi energy. Current is proportional to ρ sub s times E sub f times the exponential distance term. This led to a key insight. The Scanning Tunneling Microscope doesn't just map topography, it maps electronic structure. This was revolutionary. The second major anomaly appeared when scanning certain surfaces. Regular oscillating patterns appeared that had no correspondence to the atomic lattice. These patterns looked like ripples on a pond, concentric circles emanating from surface defects or step edges. What were they seeing? The answer was remarkable. These were electron standing waves on the surface. Electrons confined to the surface behave as waves, and when they encounter obstacles, they create interference patterns. The wavelength of these patterns is lambda equals 2 pi divided by k sub f, where k sub f is the Fermi wave vector. This provided direct visualization of quantum mechanical wave functions. Let's look at a real data analysis scenario. Suppose we scan across a silicon surface and measure the following current values at different positions. Here's our data table. We have position, measured current, expected current from our model, and the deviation. Notice that at position 1.5 nanometers, we have a significant negative deviation. The first step in analysis is to plot the data points alongside our theoretical model. This allows us to visually identify where measurements deviate from expectations. Here's our plot. The blue curve is the theoretical model. Red dots are measured values. Notice the gold dot at 1.5 nanometers deviates significantly from the curve. Step 2 is to calculate residuals. A residual is the difference between measured and expected values. Large residuals indicate our model is incomplete. Residual equals I measured minus I model. We want to examine the pattern of residuals across our scan. This residual plot shows the deviations. Green dots indicate good agreement. The red dot shows our anomalous point. This might indicate a surface defect, a different atomic species, or a change in electronic structure. Step 3 is to refine the model. Based on the anomaly, we hypothesize that at position 1.5 nanometers, there's an atom with different electronic properties. This process exemplifies the scientific method in action. Measure, model, find anomalies, refine, repeat. Let's summarize what Binnig and Rohrer taught us about scientific discovery. Lesson 1. Precise measurements are the foundation of discovery. Binnig and Rohrer achieved sub-angstrom precision, allowing them to see what no one had seen before. Lesson 2. Models are essential for understanding data, but we must be willing to revise them when anomalies appear. The initial tunneling model was good, but incomplete. Lesson 3. Anomalies are not failures. They're opportunities for deeper understanding. Every deviation from the model tells us something new about the system. Lesson 4. Science is iterative. Your first model will be wrong. Your first measurement will have artifacts. Refine, improve, iterate. Let's work through a final practical exercise that ties everything together. Suppose you scan across a surface and measure these current values in nanoamperes at positions 0, 1, 2, 3, and 4 nanometers, 2.5, 1.7, 1.1, 0.7, and 0.5. Here's the data table with the natural logarithm of current. Why compute the logarithm? Because the tunneling equation is exponential. If we take the natural log of both sides of the tunneling equation, we get log I equals log I0 minus 2 kappa d. This is a linear relationship. When we plot log current versus position, we get a straight line. The slope gives us negative 2 kappa. From this data, we can extract the decay constant and verify it matches theory. The slope is approximately negative 0.4. This means 2 kappa equals 0.4, so kappa equals 0.2 per nanometer, or 2 per angstrom. This value is quite reasonable and matches expectations for typical metal surfaces. This confirms our measurements are consistent with quantum tunneling theory. The work of Gerd, Binnig, and Heinrich Rohrer exemplifies scientific excellence. They combined theoretical insight, experimental skill, and persistence to achieve something extraordinary. They taught us that atoms are not abstract concepts. They are real, physical objects that we can see, manipulate, and study individually. They showed that careful measurement, guided by theory but open to surprises, leads to discovery. Anomalies in data are not nuisances, but invitations to deeper understanding. They demonstrated that breakthrough science requires bringing together multiple disciplines. Quantum mechanics, materials, science, electronics, and mechanical engineering all contributed to their success. As you pursue your own scientific investigations, remember the lessons from this case study. Measure carefully. Every detail matters when working at the frontiers of knowledge. Build models to interpret your data, but remain skeptical. Models are tools, not truth. When you find anomalies, celebrate them. They are opportunities to learn something new. Finally, communicate your findings clearly. Science advances through sharing knowledge. Binnig and Rohrer's work had impact because they published their results and taught others their techniques. Science is not a collection of facts. It is a process, a method for discovering truth through careful observation, measurement, modeling, and critical thinking. The Scanning Tunneling Microscope is a perfect example of this process in action.